All right, chapter 9, problem 27. A uniform rod AB of length 5 meters and mass 3.8 kilograms is hinged at A and held in equilibrium by a light cord as shown in figure 9-67. A 22 Newton load hangs from the rod at a distance d so that the tension in the cord is 85 newtons. A, draw a free body diagram for the rod. B, determine the vertical and horizontal forces on the rod exerted by the hinge. And C, determine D from the appropriate torque equation. So I already have a free body diagram set up here. Let's just go through that real quick. So a couple things let's mention right off the bat, actually, that I forgot to write. Theta is given in the problem. This is 53 degrees. Phi is also given in the problem. This is 37 degrees. And so theta minus phi can be calculated very easily. Other than that, let's go from the left to the right on the free body diagram and just go through everything. So at the bottom left corner, we want to have the hinge exerting a force on the rod. So I would think probably it would affect it this way, but let's see as we carry it through the problem. We talked about the angle already, and this is just breaking them into components, so who knows where the hinge's force is until after we've calculated it. This could be FH or this. So the next one is the load pointing downwards, the center of mass pointing downwards, and the force associated with it. And then at the top we have the force from the rod. So this total, let's talk about this angle real quick. So this total angle is theta as well. This is why we're allowed to say theta minus phi for this smaller section at the bottom here. And whenever the triangle is flipped, kind of in the way that this top one is, then you may end up with some weird trig stuff, like a sine going with x and cosine going with y. So you just have to be wary of those kinds of things. This is how you'll set up the triangle, just like this, with phi at the bottom left corner of the triangle and fr as the diagonal. X is still going to be in the x direction and y is still in the y direction, but now that they've flipped, in a sense, like from below the x-axis to above almost, it makes it so the adjacent leg is the y leg for cosine, and then the opposite is x. So in any case, we have equilibrium here, and that means that we're allowed to use some of the forces equal to 0, some of the torques equal to 0, and learn some stuff from that. So let's look at that. So sum the forces to 0, and let's look at just the y forces for now. So just the y forces, we have the y component of the hinge force, we have the y component of the rod force, and then we have 2 negative y's as well. So 2 positive y's, 2 negative y's, and that's what we have in our equation. So you just move everything over that you need, and then keep one thing on one side. Like if you're looking for FHY, then just move everything else to the other side, so on and so forth for any other variables. So you just do some algebra, and you should find that this is minus 9. This is negative 9 newtons, the y component of the force exerted on the rod by the hinge. Then if we look at the x components, we don't have as much work to do. We just have this x component here and this x component here, right? So it's just the hinge and the rod x components. So they cancel each other, and you should end up with 51 newtons.